Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2020. This is a MCQ having 2 marks. The topic of the question is quantum mechanics. The question is, the operator Sx cap denotes the spin operator defined as Sx cap equals to h cut by 2 times the matrix 0, 1, 1, 0. Which one of the following is correct? There are 4 options given. Option A, the eigenstates of spin operator Sx cap are up spin equals to 1, 0 matrix and down spin equals to 0, 1 matrix. Option B, the eigenstates of the spin operator Sx cap are up spin equals to 1 by root 2 matrix 1 minus 1 and this will be down spin. Down spin is equals to 1 by root 2 times the matrix 1, 1. Option C, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining up spin is 1 by 4. And the last option, option D, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining the up spin is 2 plus root 3 divided by 4. So among the 4 options, we have to choose the correct one. Let us see how to solve this problem. So it is given in the question that the spin operator, that is the x component of spin, Sx cap equals to h cut by 2 times this matrix 0, 1, 1, 0. Now this matrix 0, 1, 1, 0 can be written as sigma x, which is one of the Pauli matrix. So Sx cap equals to h cut by 2 times this Pauli matrix sigma x. Now we have to find what are the eigenvalues and eigenvectors for the spin operator Sx cap. So essentially we will find the eigenvalues for sigma x. Then we can easily find the eigenvalues for Sx cap operator. So essentially we will find the eigenvalues for sigma x, then we will multiply h cut by 2 with the eigenvalues of the sigma x or the Pauli matrix. So for that, what we have to do, we have to calculate this determinant, that is sigma x minus lambda times I2. So here lambda is the eigenvalue of the Pauli matrix sigma x and I2 is the 2 cross 2 unit matrix, and this determinant should be equal to 0. So if we write this whole thing in the matrix form, then it will become determinant of this matrix 0, 1, 1, 0, that is the sigma x matrix, minus lambda times the I2 matrix, that is 1, 0, 0, 1, that is equals to 0. So it will basically give determinant of minus lambda 1, 1 minus lambda equals to 0. So we will get lambda squared minus 1 equals to 0. So lambda equals to plus minus 1. Hence the eigenvalues for the Pauli matrix sigma x are plus minus 1. So we will denote lambda plus equals to plus 1 and lambda minus equals to minus 1. These are the 2 eigenvalues for sigma x. So the eigenvalues for this operator Sx cap will be basically h cut by 2 times lambda plus and h cut by 2 times lambda minus. So the eigenvalues of this spin operator Sx cap are plus minus h cut by 2. Now we will find the eigenstates for this spin operator Sx cap. Let us consider uv represents the eigenstate of Sx cap. So it is also known as spinor. To find the eigenstates, what we will do, we will consider this Sx operator times the eigenstate uv equals to the eigenvalue, that is plus minus h cut by 2 times the spinor or the eigenstate uv. Now Sx cap is basically h cut by 2 times the polymetric sigma x. So from both sides we can cut the h cut by 2, and sigma x is 0 1 1 0. Then we can multiply this 0 1 1 0 matrix with the column matrix uv, and that is equals to plus minus uv matrix. So it will give vu matrix equals to plus minus uv matrix. So we will get v equals to plus minus u. For the eigenvalue plus h cut by 2, we will have v equals to u. For the eigenvalue minus h cut by 2, we will have v equals to minus u. Let us choose u equals to 1. Then v equals to 1 for the eigenvalue plus h cut by 2, and v equals to minus 1 from this equation for eigenvalue minus h cut by 2. So eigenvectors or eigenstates for the spin operator Sx cap will be 1 1 and 1 minus 1, but they are not normalized. So in the normalized form, the eigenvectors or the eigenstates for the spin operator Sx cap will be up spin, that is 1 by root 2 times the column matrix 1 1, and the down spin, that is the 1 by root 2 times 1 minus 1 matrix. Now if any spin state, that is the state or kth of phi, is given, upon the measurement of the spin operator Sx cap, the probability for obtaining the up spin state or down spin state of the x component is mod square of the inner product between up spin and phi state, or mod square of inner product between down spin and phi state. Now let us check the options given one by one. So option A, that is given the eigenstates of the spin operator Sx cap are up spin, that is 1 0, and down spin, that is 0 1. So this is false because we have already calculated the eigenstates or eigenvectors for the Sx cap operator is 1 by root 2 times the column matrix 1 1, and for down spin, that is 1 by root 2 times the column matrix 1 minus 1. So this option is false. Now option B is given, the eigenstates of this spin operator Sx cap are for up spin, that is 1 by root 2 times the column matrix 1 minus 1, and for the down spin 1 by root 2 times the column matrix 1 1. So this is also false because for up spin it will be 1 by root 2 times the matrix 1 1, and for down spin it will be 1 by root 2 times the column matrix 1 minus 1. So option B is false in this case. Now option C, it is given that in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap, the probability for obtaining up spin is 1/4. So in our case, the given state phi is 1 by 2 times the matrix 1 root 3, and up spin state, that is 1 by root 2 times the column matrix 1 1, that we have calculated in the previous slide. Now in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap operator, the probability for obtaining up spin state is given by P equals to mod square of inner product between the up spin state and the phi state, that is 1 by 2 times matrix 1 root 3. So this bra of up spin will give this row matrix, that is 1 by root 2 times the row matrix 1 1, and the state of phi state, that will be 1 by 2 times the column matrix 1 by 1 root 3, and we have to take mod square of this. So we can take out this 1 by 2 and 1 by root 2 from this mod square. So it will give 1 by 2 root 2 whole square times mod of the multiplication between these two matrix 1 1 and 1 root 3 and mod of this square. So this will give 1 plus root 3 mod square whole square, and this will give 1 by 8. So we'll get effectively 1 plus 3 plus 2 root 3. So this is the 1 plus root 3 whole square divided by 8. So it will give 4 plus 2 root 3 divided by 8, and after simplification it will give 2 plus root 3 divided by 4. So it is not matching with our option C. So option C is false in our case. Now option D is saying in the spin state 1 by 2 times the column matrix 1 root 3 upon the measurement of Sx cap, the probability for obtaining upspin state is 2 plus root 3 by 4. So this is true because we have already calculated this probability in the option C, and from the option C we have found that the probability will be 2 plus root 3 divided by 4. So the option D is correct in our case. So according to our solution, the last option D, that is in the spin state 1 by 2 times matrix 1 root 3 upon the measurement of Sx cap operator, the probability for obtaining the upspin is 2 plus root 3 divided by 4. So this is the correct one for this question. This question is from the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is electromagnetic theory. The question is, a sinusoidal voltage of the form V as a function of time t equals to V0 times cosine of omega t is applied across a parallel plate capacitor placed in a vacuum. Ignoring the edge effects, the induced EMF within the region between capacitor plates can be expressed as a power series in omega. The lowest non-vanishing exponent in omega is. So let us see how to solve this problem. It is given that a sinusoidal voltage of the form V as a function of time t equals to V0 times cos omega t is applied across a parallel plate capacitor. Let the separation between capacitor plates be small d. So it is shown in the schematics that two plates of the capacitors are separated by the small distance small d, and we have considered a small circular loop at the center having radius small r, and the area of the loop is given by the shaded region here. So we will calculate the induced EMF along this circular loop. So the electric field between the plates of the capacitor is E equals to the applied voltage along the capacitor plates, that is V as a function of small t, divided by the separation of the capacitor plates, that is small d. So the time varying electric field between the capacitor plates is given by E as a function of small t equals to V0 divided by d times cos omega t. We know that according to the Maxwell's theory of electromagnetic induction, if a time varying electric field exists in a region, then there will be a time varying magnetic field associated with that time varying electric field, and that is given by the Maxwell's equation curl of the magnetic field B equals to mu naught times epsilon naught times daily del T, where mu naught is the magnetic permeability in the vacuum, epsilon naught is the electrical permittivity in the vacuum, and E vector is the electric field vector that is coming here due to the applied time varying voltage across the capacitor plate. Now we will take the surface integral both sides of this equation. So it is given by surface integral of the curl of B vector equals to mu naught epsilon naught times surface integral of daily del T. Here the surface is considered by the surface area of the small loop of radius smaller that has been shown in the schematic in the first slide. Now we can convert this surface integral into the closed path integral. So that is given by closed path integral, line integral of the B vector equals to mu naught times epsilon naught times surface integral of daily del t times the ds vector. So here the line integral part will give b times 2 pi r. Here 2 pi r is the circumference of the small loop having radius small r that we have considered in the first slide. And that is equal to mu naught times epsilon naught times this daily del t, that will give minus v naught omega divided by small d times sine omega t times the surface area of the circular loop, that is pi r square. So from this we can find the associated magnetic field, that is B equals to minus R times mu naught times epsilon naught times V naught divided by 2 small d times omega times sine omega t. So this is the expression for the time varying magnetic field associated with the time varying electric field between the capacitor plate. Now, according to the Faraday's law of electromagnetic induction, we know that if a time varying magnetic flux exists in a region, then there will be a induced electromotive force, and that is given by induced EMF E equals to minus d phi dt. Here phi is the time varying magnetic flux in the region. So the induced EMF E equals to minus d dt of the magnetic flux, that is given by magnetic field B as a function of time times the area of the region. So A is the area within the region between the capacitor plates here. Now area is constant here, so it can come out from the derivative. So E equals to minus A times d dt of the magnetic field. Now we have calculated the magnetic field associated with the applied voltage across the capacitor in the last slide. So this d dt of B will give here as E equals to A times, that is the area, times R mu naught epsilon naught V naught divided by 2t times omega square cos omega t. Now the terms in the parentheses are independent of omega, so we will not write it again and again. We will consider the omega dependent part here. Now we will expand this cos omega t in the power series. So this expression will give E equals to this term times omega square times the power series of the cosine of omega t, that is 1 minus omega t whole square by 2 factorial plus omega t to the power 4 by 4 factorial plus so on. Now we will multiply omega square with this series, so this will give omega square minus omega to the power 4 t square divided by 2 factorial plus omega to the power 6 times t to the power 4 by 4 factorial plus so on. So we can see the lowest non-vanishing exponent of omega is 2. Therefore, the lowest non-vanishing exponent in omega from this expression is coming out to be 2 here. According to our solution, the lowest non-vanishing exponent in omega is 2. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is quantum statistics. The question is, consider a gas of hydrogen atoms in the atmosphere of the sun where the temperature is 5800 Kelvin. If a sample from this atmosphere contains 6.023 times 10 to the power 23 of hydrogen atoms in the ground state, the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power n, where n is an integer. The value of n is, so basically we have to find the integer value of n in this 8 into 10 to the power n. One information is given here, that is Boltzmann's constant value is 8.617 times 10 to the power minus 5 electron volt per Kelvin. So now let us see how can we solve this problem. It is given in the question that a gas of hydrogen atoms in the atmosphere of the sun where the temperature is T equals to 5800 Kelvin. Now we know the energy levels of the hydrogen atom is given by E with the subscript N equals to minus 13.6 divided by N square electron volt. Here N is the principal quantum number that takes the values 1, 2 and so on. Now the ground state energy of the hydrogen atom is given by E1 equals to minus 13.6 divided by 1 square. So here the principal quantum number value will be 1 and that will give minus 13.6 electron volt. And for the first excited state, the principal quantum number value N equals to 2. So the energy of the hydrogen atom in the first excited state is given by E2 equals to minus 13.6 divided by 2 square, that is minus 3.4 electron volt. According to the Maxwell-Boltzmann distribution, the number of classical particles in an energy level E at temperature T is proportional to N as a function of, that is, number of the particles as a function of energy is proportional to e to the power minus E by kBT. Here kB is the Boltzmann constant. Let N1 and N2 be the number of hydrogen atoms in the ground state and the first excited state respectively. So N1 divided by N2 will give e to the power minus E1 divided by kBT whole divided by e to the power minus E2 divided by kBT. So this will give e to the power E2 minus E1 divided by kBT. Here it is given that N1 equals to 6.023 times 10 to the power 23. N2 equals to 8 into 10 to the power n. Here we have to find this n value. And temperature is 5800 Kelvin. And we have already from the calculation, that is E2, that is the energy of the first excited state is minus 3.4 electron volt. Energy of the ground state of the hydrogen atom is minus 13.6 electron volt. So E2 minus E1 is 10.2 electron volt. Now we will find the thermal energy value at the temperature T equals to 5800 Kelvin in electron volt. So kBT equals to 1.38 times 10 to the power minus 23, that is the value of Boltzmann constant, times 5800 Kelvin, and the unit of the energy will be joule here. To convert it into the electron volt, we have to divide it by the electronic charge, that is 1.6 times 10 to the power minus 19. So this kBT value in electron volt will be 0.50025 electron volt. Now we will use the equation coming from the Maxwell-Boltzmann distribution, that is N1 by N2 equals to e to the power minus E2 minus E1 divided by kBT. So we will put the values of N1, N2, E2 minus E1 and the kBT value. So N1 is 6.023 times 10 to the power 23 divided by N2 value is 8 into 10 to the power n equals to e to the power 10.2, that is E2 minus E1 divided by kBT value in electron volt, that is 0.50025. So this will give 6.023 times 10 to the power 23 divided by 8 into 10 to the power n equals to e to the power 20.3898. Now the exponential part will give 7.16 times 10 to the power 8. From here we can write 10 to the power n equals to 6.023 times 10 to the power 23 divided by 8 into 7.16 times 10 to the power 8. So this will give approximately 10 to the power 14. So the n value will be 14 in the integer form. So we have discussed the solution for this problem, and we found that the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power 14. So the n value in this question is 14.